So this first process in activity 212 is how we look at a circuit that has AND gates, OR gates, and inverter gates, and directly from that circuit, convert it to a truth table, and then tack on the step you did in 211 of taking that truth table and writing it as a logic expression. So the first thing that this process requires you to do is add a test point at the output of every gate. So as you look at the circuit, every time there's an AND gate or an OR gate or an inverter, you're going to put a test point, which means basically putting a probe in. I mean, you could use a buzzer or whatever, but generally speaking, we just put a probe in so that if it's a zero, it's the probe's off, and if it's a one, the probe is on. So we can basically just visually see whether there's a hot or an off, a high or a low signal coming on the backside or the afterward side of the gate. Then in the truth table, we have to add columns. So we've already learned how to count in binary and create your input columns. And then you just tack on one more column for your output. But now we're going to add columns to that, one column for every one of those test points. And then from that, you're going to start at the input of the circuit and work your way through the circuit, figuring out what the test point would indicate. And so this part C, some of you will be able to very easily look at the circuit and process it mentally, and that's what we're going to do in class. And by doing that, you can just quickly figure out what each test point would be. Others of you may struggle with that a little bit. So this part C is what I was mentioning earlier. You can go into Multisim and just build the circuit and then just run it. Change the switches and see what each test point indicates. So if you need to do that for one or all of them, you can just build the circuit. It's a pretty simple circuit for all the problems you're doing. And you can just actually literally make the circuit show you with test points, with probes. Once you figured out what each test point indicates, from that, then you're going to determine what is the output. Would the output be on or off? And then you're going to determine what the min terms would be, those minimally satisfied terms. Anytime there's a 1 in the output column, in other words, you're going to figure out what those min terms would be where it is a 1. And then using those min terms, write your sum of products expression for that logic circuit. So those are the 5 steps. It may not completely make sense without seeing an example, so that's what we're going to do next, is run through an example to help you visualize it. And then when we're done with that, we'll look at the second technique of going from a circuit to an expression to a truth table. All right, so let's look at an example here. All right, so if this was the circuit that we were analyzing, you can see there's 3 inputs. And the way you would, if you were going to use the multi-sim to create the circuit, over here by these X, Y, Z inputs, you would want to make those switches so you could turn them on or turn them off. And then you just put an inverter in and AND gates. Remember, the bullet shapes are AND gates and the shield shapes are OR gates. So just remembering back the inverter gate, if this is on, the inverter switches it to an off. And if the input is off, the inverter switches it to an on. The AND gates only give a high or on output if both of the inputs are on. And so they have to both be on to pass an on signal through. And then in the end here, this last shield one, the OR gate, if either one of them is on, the output will be on. So this is a fairly simple 3 input circuit with a single output, but with those inputs traveling through a sequence of combined 6 gates. And we're going to see this circuit multiple times as we kind of work our way through the process. But as you look at it, the whole goal is to then put test points after each gate. So like we said in step 1, put a test point after each gate. So here's what that same circuit would look like once we put a test point in. And again, that test point could be a buzzer if you wanted to hear it. Generally speaking, we just put probes. And that's what you've done on all your circuits so far, is just use a probe so you can see if it's giving you a high or a low output. So you would just put test point 1 right after this one, test point 2 right after this one, and the sequence of them doesn't matter. You just have to be consistent. So if this is test point 1, as you fill in the first row of your table, it needs to stay test point 1 all the way through. So you definitely want to make sure you always go through them in the same order, whatever order you choose. And typically speaking, it is easier if you follow kind of one branch all the way to the end and then follow the second branch all the way to the end if you're able to, like this one is. So here's our circuit. And if we put switches over here, we could turn the X and the Y and the Z on or off. So you can see in the first row of our truth table, we're just starting at binary 0. And you can see for the inputs, the X, Y, Z inputs, those 3 columns can just automatically be filled in. We have 3 inputs, so that means we're going to have 2 to the 3rd power outputs, or not outputs, but 2 to the 3rd power combinations. And so we should count from 0 to 7 in binary. And so if you look at the rows, we got 0, 1, 2, 3, 4, 5, 6, and 7 counts. And then we've got our column for the output, which we're going to figure out. And then we've got a column for each test point. And so what you have to do is say, okay, well, right now on this first row, X is off. So once that off signal goes through the inverter here, the test point 1 is going to read on because the inverter inverts the signal. So since X started as off, test point 1 is going to signal on. Since Y is off, looking at this AND gate, we're going to have an on coming from the X line, but we're going to have an off coming from the Y line. Does that make sense? Maybe if I draw it on here, it'll make sure we're all on the same page here. So if this is 0, 0, 0, here it's going to be on. This is going to be 0. So if you have a 1 and a 0, the output's going to be a 0. Okay, so that's basically what you're doing, is trying to think through what the inputs and outputs would be. Z is off, so we're going to have 0 and 0, which means this is going to be 0. You tracking with me okay? Is it making sense? See a few people kind of nodding, sort of, maybe. All right, so if we look at test point 4, it's after this inverter. That inverter is fed by the Y line. You can see it goes up and connects to the Y line. So you've got a 0 coming in, which means it's going to be a 1 coming out. The inverter switches the signal. But the bottom of this AND gate is coming all the way from the X, which is off. So you've got a 0 here. If it's a 1 and a 0, the output is 0. It only gives you an on if they're both on. It's an AND gate. So the top and the bottom inputs both have to be on for it to give you an output of on. Now, if we look at this final gate, this is an OR gate, right? So if either test point 3 or test point 5 are hot, if they're either one of them is a high, the output will be high. But in this case, they're both low, so the output would be low. So I just record in the row here, test point 1 would give me a high, test point 2 would give me an off or a low, test point 3 would be a low, test point 4 would be a high, and test point 5 would be a low. And since neither test point 3 or test point 5 is on, since they're both low signals, the output would be a low signal, an off. So if we think about this output here, it's going to be a 0. Any questions about how I'm tracking it through the circuit? Is that making sense okay? See a few people nodding. Okay, we'll practice a little bit more. So basically from this conclusion, both P and 0.3 and 0.5 are off. Therefore, my output here is off. All right, let's try this second one. I'm going to ask for feedback from you guys here. So now we're looking at the second row. So we're saying the X is still off, the Y is still off, but the Z is on, right? 0, 0, 1. We're looking at this, right? That's our inputs. So Cohen, what would test point 1 show me based on this X input being off?
Would it be 0?
If we've got 0 coming in, what does the inverter do?
Oh, then it'll switch it to 1.
Right. So that's going to be a 1. Okay. So we're going to be 1 right there. All right. And so that's a 1 because the inverter switched it, but this Y coming in is just going to be still 0. So Nico, what's test point 2 going to say since there's a 1 and a 0 coming into that AND gate?
0.
0, right? They both have to be on. So that's going to be a 0. Okay, so now we know that's 0. And then Z is on. So based on our binary count here, Z is on. So we've got 0 and 1. So Carson, what's test point 3 going to show me if I've got a 0 and a 1?
Is it going to be 0?
Yeah, it's going to be off. It's going to be a 0. So test point 3 is going to be a 0. All right. And if we go down to the bottom, this line, it comes from the Y, right? So we've got a 0 coming in. So Michelle, what's the test point 4 going to show me?
1.
1. All right. And then this bottom line is, if you track it backwards, it's coming all the way from the X, right? It's tapped into the X line. So that's going to be a 0. So Patrick, if we've got a, on this AND gate right here,
Yeah.
we've got a 1 and a 0, what's test point 5 going to show?
The 0.
Yeah, since they're not both on, and means they both have to be on. So since they're not, we get an off. And so test point 5 is an off. And since this is an OR gate, we're basically looking at test point 3 and test point 5 because those are the two inputs. If either one of them is on, our output will be on, right? But in this case, they're both off. Both test point 3 and test point 5 are off. So Jason, what's the F1 going to be for this sequence?
0.
0. Questions about that one? All right. We'll do one more together, and then I'm going to have you start to try some on your own. All right. So if there's our result. We figured that out. Now let's do this one. So now we're looking at this input, 0, 1, 0. So X is off, Y is on, Z is off. That's our input. All right. So let's see who I need to pick on some of the people. Andy. If this X line has a 0 coming in, what's test point 1 going to read?
Would it be a 1 since it's an inverter?
Yep, it's going to flip that. So it's going to be a 1. And then now we've got a Y. Here it's Y is 1. So let's see, Carter, what's test point 2 going to give me?
That would be a 1.
Yeah, we've got a hot and a hot, and on and an on. So they're going to give me a 1 there. All right, making sense so far? Okay, so now I look at this AND gate. I've got a 0 coming from my Z. So that AND gate has a 1 and a 0 coming in. So Harry, what's the test point 3 going to read?
0.
0. All right. If I go down to this bottom row, this line is connecting right there, right? So that's a 1 coming in. So Evan, what's test point 4 going to read?
0.
0. If it's a 1 coming in, it inverts it, makes it a 0. This line, if I track it back, it's connecting into the X line. So it's 0 and 0. So I think, Devin, what's test point 5 going to read if these are both zeros?
0.
0. All right. And now I'm looking at test point 3 and test point 5. One of them has to be on. Since this is an OR gate, either one of them can be on to give me an output. What's the output going to be? Anybody?
Zero.
0.
Yeah, I heard a bunch of you at once. Good. I think you're starting to get the idea. We'll just do a couple more, but we won't do them together. I'll have you try them and then we'll check your work. All right, so that's how you're going to have to track it through. to me, I think it's easier to write it. Some of you are strong enough with this kind of logic and thinking, you can probably do it without writing it out. Some of you may need to actually build the circuits for a while and put the probes in so you can visually test it. That's just up to you how you need to do it. All right, so we figured that one out. All right, so now try the next one, this next line. So I want you to figure out the next line that's empty. So we're looking at X is 0, Y is 1, and Z is 1. All right, so figure that out. Put your answer in the chat when you think you know what all the test points are. So don't, yeah, just put the 5 test points in for now. And you can just put 0s and 1s. So you don't have to put TP1, just put them in this same order and just put the 5 test points in the chat when you figured that out. All right. Got a little bit of variety here. So I'll go ahead and reveal. We should get 11100. 11100. And then because test point 3 is on this time, our output, our F1 is going to be 1. Questions about that one?
Yeah, if it's an AND gate, wouldn't it be oh wait, is X off? Wait, no, but oh, okay, never mind then.
You got it?
Yeah.
So yeah, the last gate's an OR gate. So only the 3 or the 5 has to be on. In this case, the 3 is. So our output will be on. Okay, try the next row, the 100, and then put your answer in the chat. All right, seeing more consistency this time. And we do have 00011. So what's the output? What's the F1 going to be?
0.
If test point 5
Oh,
is
never mind,
on,
never mind. Sorry, I forgot that that was an OR gate, not an AND gate.
Yeah, that's the thing that gets a little bit tricky if you're not careful. The first ones are inverters and ands, but the very last one's an or. So since test point 5 is hot, the 3 doesn't have to be, just either the 3 or the 5 has to be. Okay, one last one. Try the 101 and we'll finish with that. All right. So we're getting a lot of consistency again. So interesting that even though it's a different input, it's binary 5 instead of binary 4, we still get the same output sequence. We still get hot on 4 and 5. And so what's the F1?
1.
1. All right. So I won't have you do the rest in the chat. We'll just show them. If you go through these last two sequences, they end up all showing zeros. None of the test points will turn on. And so therefore the function will give an output of 0. So only 3 of the values, only 3, 4, and 5 inputs, the binary 3, binary 4, and binary 5, those are the only inputs that give us a hot or a high output. All right, so that's the first step. Add the test points, logically think it through, figure out what the test points would show you, and then from those test points, conclude what the output would be. All right, so once you have that, we know all of this, now we need to figure out what the min terms will be. All right, we've got all our outputs, we've got all our test points figured out. So the min terms are just these 3. And so when it's not X, Y, Z, that gives an output of 1. When it's X, not Y, not Z, that gives an output of 1. And when it's X, not Y, Z, that gives an output of 1. Those are the only 3. And so we've got our sum of products expression, just putting them together, those 3 min terms separated by plus signs. So the last part of the step's pretty easy. It's figuring out the test points, and it's really easy to make a mistake on those test points if you're not careful. You have to take your time. I prefer to actually write it down or build the circuit. It's really easy if you're trying to do it all in your head to make a mistake. And if you make one mistake, that's going to throw off a min term. And if a min term's wrong, your sum of products is going to be wrong. So you do have to be pretty careful with this. That's partly why I'm giving you today and then all of Thursday. So if you need to take your time, if you need to build the circuits to test it, if you need to draw them out by hand and write on it, like I was doing, what a lot of students like to do when we were in class is to grab a small whiteboard, draw the circuit on the whiteboard, and then with a different color marker, put all those zeros and ones on there to track it, and then erase them and do it again, and erase them and do it again. And so a lot of students like to do that, and it can be helpful. But you can also just build the circuit on Multisim, put test probes on, run it through your binary counts, and do it that way as well. Any questions about the process? All right, so it's not hard really, it's just more tedious, and you have to be really careful. It's easy to make mistakes. All right, now the second method is much quicker. If we go the other direction, from instead of going from the circuit to the truth table and then the expression, go from the circuit to the expression and then the truth table. There's only 2 steps. So I'll give you a couple of minutes to get these 2 steps written down in your notes.
Hey, what number was this again? Was this like 2, 1, 2?
Yes.
Okay, just making sure.
All right. So the advantage of this process is it's more time efficient. The disadvantage is you can't really just build the circuit and see what it's going to be at every single point within the circuit. You can only see the output, at least in terms of expressions. So this one, if you're wanting to write the accumulating expressions, you really have to do it just by hand or on paper. Whereas with the previous one, you can actually just build a circuit and have little probes tell you but the advantage of this one is it is quicker. So here we're going to still work from the inputs to the outputs, but after every gate, instead of putting a probe, we're just going to write down what the expression would be just at that one point. And we keep accumulating the expression as we move through the circuit. And then once we have the logic expression derived from the circuit, then we work backwards to create the truth table. So step B in this two-part process is basically what you learned in 2.1.1. What if you have an expression, how do you create a truth table from it? So part A is really the only new part, and then part B is just adding what you did in 2.1.1. That's why I wanted to try to get 2.1.1 and 2.1.2 done together before the break, because they really go hand in hand. So any questions about that before we look at an example? All right. So for the example, we're just going to, again, look at a circuit and walk you through the steps. So here is our circuit. And you can see they're just using the same circuit here. But the idea is that anytime you see an AND gate, you're going to think about those expressions being multiplied, okay? So no plus sign between them. And anytime you see an OR gate, you're going to think about those expressions being added, right? It'll make sense when you see what how that shakes out. So thinking through not a 0 or a 1, if this input is X, what's the output just in terms of letters?
Y.
No, it has to still be X, but
Not X?
not X. Yeah, there we go. So that's how you're going to do this is if the input is X, it's going to invert it to a not X. So if it was a 0, it makes it a 1. If it was a 1, it makes it a 0, right? But instead of writing 1s and 0s, we're just going to write X's and not X's, Y's and not Y's. So if we walk through this circuit, if this is X, after it inverts, it's not X. If this is Y, we've got a not X coming in with, whoops, forgot to turn on the pin. We've got a not X and a Y coming in, so the output is not XY. And then here, it's not XY output. This is a Z. So the output is not XYZ. On the bottom part of the circuit, this one tacks in right here. So if that's a Y input, the inverter makes it a not Y. The bottom line tacks in up here. So we've got a not Y with an X. So just putting them in alphabetical order, the output would be X, not Y. So now over here, we've got an X, not Y, and a not X, Y, Z. So, but where they're running through an OR gate. When we write it as an OR gate, we put a plus sign between it. And so by doing it this way, we're actually generating the sum of products expression from the circuit itself. So you can see we're already done. It's much quicker than test points and all that. But you can't see not X and not XY, and you can't see these steps in an actual circuit. So this is something you basically have to do on paper or in your head, whereas the other one, you can't actually do it with a circuit and test it. Questions about the process here? Does that make sense? How to just look at each gate and accumulate the signals all the way till the end? The outputs that come from an AND gate they look like they're multiplied together. So not X times Y, not X times Y times Z. We don't put a multiplying symbol between them, but that's kind of what it looks like. And then when they're coming through an OR gate, we put a plus symbol between them, which is a little confusing because in math, a plus sign usually means and, but here an OR gate is what gives us the and, or gives us the addition symbol. All right, once we have that min-term sum of products, we just do what we did in the 2-1-1 assignment. So we've got our not X, Y, Z, which is only this row. And we've got our X, not Y, which fits both of these rows. So we just create our truth table from this min-term expression. So that's just, this last step is just a repeat of what you were doing in the 2-1-1 activity. Any questions about that? All right, in activity 2-1-2 on the website, you're going to be going through this process. The first part of it does the first thing with the test points and creating the table, and you just need to answer the questions the way they're asked. If you want to do this second strategy on the side to check your work, you can, but you need to answer the questions the way they're asked. Okay, so now that you know both methods, you can't just use the second method all the way through. You have to use the method that they're asking you to use. And then the second part of the assignment asks you to do what we just learned, using the expressions method. And then there are some conclusion questions to answer. So if you look on OneNote within Teams, you'll see an assignment 2-1-2, and the things you need to include for full credit are the notes and the answers to all the questions and the conclusion. Any questions about the assignment today or the lesson we just covered? All right. You've got about 35 minutes to work. If you want to stay online in case you need help, you're welcome to. If you want to log off and work on your own, that's fine as well. If you want to check back in and let me know where you're at, that's fine. But since we also have the work time on Thursday to work together, I won't require a check-in. I will keep the Zoom running though. So if you do log out and you run into trouble, you can come back on and ask questions at any time. I'll just keep it running until 9:50. So you can stay or you can go, either one. If I don't see you again this morning with any questions, I'll look forward to seeing you for our last class period on Thursday. But if you're sticking around, I'll be here for you to help. Have a great day if I don't see you.
Thank you.